So let's start the Unconference Summaries. Ozzy, are you here? You ready to do the spectroscopy, or do you want a moment? Okay.
Yes. Okay. So we had a great spectroscopy unconference session. Eric talked about the history of spec utils and how we've been working on this since the 2012 AstroPy coordination meeting. I was in that, I remember. And we've been waiting for this to happen, but it's been really slowed down by a lot of things in sorting out WCS interactions and what is the most general form and how should we put everything together. We then pointed to the APE, which is like an AstroPy definition document, which defines spec utils and what we want in spec utils, which is currently a one-dimensional object called spectrum 1D. And within this APE are a list of different things that we want to implement in spec utils to deal with this spectrum 1D object. And so at the end of this list is a list of possible hack ideas. And some of those can just be implementing the things in the APE. So Spectrum 1D has things like a mask versus a bit flag, which just gives you true, false, or more flexibility in defining like this is a cosmic ray, this is a bad pixel, things like that. We hope to one day be able to connect the Spectrum 1D to IFUs and other data cubes, but that isn't currently possible. And we talked about how you can think about these three-dimensional objects as a collection of 1D spectra. And we also talked about the possibility to expand just from having like a wavelength that represents the center of a pixel to represent the pixel edges or bin edges, and that application to X-ray astronomy and solar astronomy. And we also had a really nice discussion about the development process and how we can use people that are writing pipelines, either the JWST development pipelines or the KEC pipelines or other pipelines, and the institutional support for those pipelines, but then build more general packages like spec utils or something. And is it possible to make things so modular that we can combine these things and maybe put forth something that is community driven, but also serves the needs of the institutions that are building them. And so we're hoping, we also talked about there's, in addition to spec utils, there's spec reduce and spec viz, which are much more nebular still. And so we talked about possibly having a breakout session, some timeline for at least spec reduce. And I think spec viz is also maybe a whole nother discussion that will come up in different lightning talks. Okay, so I'm going to say I would encourage you, if you're interested in this, these are possible Hack Day projects, as well as future unconference session ideas. And take a look at these and feel free to add to them. Any questions? Okay, awesome. Then I will hand this over to Matt.
So we had about 10 people working through either a intro to GitHub or an intro to Git tutorial or a website that walks through branching, and then towards the end of that, had people fork a repository on GitHub, clone that down to their hard drive, make a branch, commit to that branch, push it back up to GitHub, and open up a pull request. The plan tomorrow is to take the last couple of steps in that process and show people how to update their local copy once changes have been made to the main version online. So that was fast, but that's what we did. And next up, Cookie Cutter. Who's talking about Cookie? Does somebody want to report out about Cookie Cutter?
So this was a sprint session. So we basically went through the open pull requests and figure out what need to be done. And some people were trying and read the documentation and identify what's missing there and what's misleading. So that's it, and it's not yet finished.
Hi there. So I'm reporting for the packaging unconference session. So this was led by Eric, and he first kind of went over different definitions. So what really is a repository? What is a package? What is a module? We learned that submodule is not a module within a module, but instead a repo within a repo. So anyway, that's important information. What? Oh, okay. We also looked at kind of a basic package infrastructure. So when creating a package, you have a README file, you have a license. So we kind of looked over that, and then also looked over kind of syntax for calling certain packages within a Python environment. We looked at some underlying motivations for why you would turn your code into a package, basically so that it can work anywhere, it can be easily imported by other people, and so that other people use it, and you can be of service to the community and have your code used. And then we talked about some versioning nomenclature, about when they say x.y.z, what do those different numbers really mean, kind of in a from a developer's point of view. And then finally we had a live demo of Cookie Cutter, where we kind of found out how to initially like initiate a package through Cookie Cutter and what information you should enter in order to kind of get all of the things that we had previously mentioned in the package infrastructure. And those are all created on their own through Cookie Cutter. So thank you very much. Who's next?
Hello, I'm Abby. So we got a tutorial from Rebecca on pandas. It's something that a lot of us were familiar with. Some people had kind of dabbled in before, but like I personally hadn't ever used it before. So I linked to just like the general pandas docs at the top here, just so people could read more if they wanted to. But this is like a general data analysis library. It's great for cleaning your data, for setting whatever you want your null value to be, for getting rid of null values, for sorting by various topics and things, and characteristics that you've given your data. So what we did, it was more of a self-guided tutorial where Rebecca had this repo that she has used to teach with before, which is is based on the data carpentry workshop, which is like software carpentry but for data. And so here is the link to the Jupyter notebooks that we were using. They were in this folder. And so we downloaded the notebooks and we downloaded the sample data sets, and then we all kind of worked through it at our own pace, and worked through the notebooks and then raised our hands when we had questions. And also I learned that you can use SVN checkout stuff even if you've never used Subversion on your computer before. It just comes with it, which is great. And this way you can download just the specific folder that we were wanting to use instead of the whole repository. So, so then also we have a couple notes in there as well. So Pandas is suitable for analysis of two-dimensional data sets like tables. Of other people also like AstroPy tables. This is kind of an alternative. You can group your data and mask them in lots of convenience functions. And grouping does not create a new version of your data frame, but it will return a group by object to work with. So it's like a different view on the same data. So you're not like copying your data over and over and over. That's it.
So I'm reporting on the Bayesian MCMC session. We talked about kind of the basic tutorial on Bayesian statistics versus frequentist sampling. Frequentist usually uses maximum likelihood, whereas the Bayesian is trying to map it out. Pretty much a basic introduction about priors, posteriors, probability of the data, etc., and how that gets manipulated around, and why you might want to actually sample your probability function, what marginalization is. Then we got a little more into the software that exists. There's PyMC3, there's Stan, and MC. And these methods, all implement different. These software all implement different methods. Things like Metropolis. Doesn't look like it's Metropolis. Did I? Okay. Metropolis, Hastings, ensemble sampling, and Hamilton hybrid MC, and Gibbs. So there's various ways of doing it. Then we talked a bit about how there's a lot of tuning involved in these sampling, and that's why it's hard to just use them as a black box. I think it's very easy to get into the wrong place. And so understanding the tools was one of the things we talked about. And so making them into a black box where we somehow connect them to, say, AstroPy modeling might be a bit worrisome. There's some tutorials or some knowledge that's needed, maybe to use them properly. And so hack ideas that we came up with is tutorials, especially on convergence, so that's a worry that came up. Gelman-Rubin statistics, which I don't know, but I'm going to learn. And maybe making AstroPy models work with MC or PyMC3. And there's various jargon involved, so you can look at the Google Doc.
Okay, wonderful. Hello, everyone. My name is Leah Fulmer, and today I will be offering a brief overview of the NOAO Data Lab. For those of you first hearing about it, the Data Lab is a one-stop shop to not only access high-value catalogs, but also to explore and analyze those data sets within the Data Lab environment. We're hoping to empower astronomers through optimized access and ease of exploration, all within a Python environment. So we're really excited to be here at this conference, and we hope to initiate some connections here. I wanted to add that I personally really believe in the Data Lab because I think it's a wonderful resource for people who are excited about doing good astronomy, but don't necessarily have the institutional power of being connected directly to a telescope or a university or any other institution that kind of already has a hand or time in collecting this type of data. So I'm really excited about how it can be accessible over many levels of profession or location, because it's all on the internet. You don't actually have to have any sort of specific software or hardware on your device. So as a general overview of the types of catalogs that the Data Lab offers, we essentially have everything that's been observed with DECCAM. So we have the Dark Energy Survey, the Survey of the Magellanic Clouds, as well as the Legacy and Plane surveys. And then, of course, we'll have DESI when it comes online. Furthermore, we have kind of external surveys, so SDSS, PHAT, and Gaia, and I'll come back to that in a minute. But then finally, we have the NOAO source catalog, which is essentially all of the public imaging data from Cerro Tololo and from Kip Peak that previously has been under the jurisdiction of individual PIs, but not necessarily public. We're making all that public so that you can access it through the Data Lab. But we not only have catalogs, we also have services. So we have a catalog and image query service through a Python query client, where you can query our data in a Jupyter notebook, and then analyze that data right there. So connected to this, we have virtual storage. So all of our users get 1 terabyte of free storage. So you can essentially save the outputs of your queries to our servers and save your Jupyter notebooks that you're using to analyze that data to our servers. And you never have to actually download anything onto your personal computer, which again makes this accessible anywhere there's internet, which is super exciting to me. So I wanted to take us through a science example really quick. So if we are trying to explore the DECCAM plane survey and we're trying to look at a particularly dusty region of the plane, we can construct and submit a SQL query that asks for specific colors and magnitudes, as well as this frac flux value that kind of says how much flux of your objects is in a particular PSF, excuse me. And then from there, we take the output of the query and format it into a pandas data frame, and then we additionally define a quality threshold using that frac flux value. And from there, we can create plots. So we have a color diagram and a color magnitude diagram. And it's really exciting about this is because we're looking at a dusty region, the output of the stars really separates itself into 2 populations, which is basically in front of the dust and behind the dust. And so this is just a really simple example of how you can use a query and analyze that query within a Jupyter notebook through the Data Lab. So if you're interested in getting started, I would encourage you to go to the Data Lab website, which I'm going to put up in a moment. You can go to Quick Start and then create a new account. You put in your information, and then once your account is approved, again, I would like to remind you that you will have 1 free terabyte of storage to play around with and kind of just go hard. So that's a really exciting service. But yeah, so for the future, we are looking to incorporate data analysis software. So not only have a place where you can access the data, but also where you can analyze it right there using what's something very similar to a desktop tool. So this here is SpecViz, which is primarily developed by Nick Earl and folks at Space Telescope. And we're collaborating with them in order to make sure that we can get SpecViz into the data lab environment so that you can call it, like, for example, from a Jupyter notebook, it pops up like a desktop tool, and then you can analyze your queried spectra right there. Furthermore, we want to have access to Jupyter Lab. So for those of you who are really in need of Jupyter Lab and really want to use it, we're hoping that you can do so soon within the data lab environment. And then finally, what's very exciting is we will have Gaia DR2 data on our servers within the upcoming weeks, so you can just submit a SQL query like we have been on the Data Zero Hack Day, but hopefully with less crashes. So that's all I have for you. Please, I would encourage you to connect with me here or to tweet or email directly to the Data Lab. And then I'm also going to propose an on-conference session for getting started with Data Lab tomorrow, so you can all have your terabyte of free space to play around with. And I would love to hear if you're interested in doing that. Thank you.
Thank you.
Okay, that seems to be working okay. All right, so quickly, I heard this morning that lightning talks could be about stuff that you're really excited about, and this is something that falls in the category for me. I'm the lead developer of this new package, which we just released a couple of months ago. Also very excited. My first package to actually get released. Yeah. So the package is NDCube. It basically what it does here is I've said it's a package for handling n-dimensional data, which is described by the World Coordinate System transformations. Just very quickly, is there anyone here who really doesn't know what World Coordinate System is? We'd usually call it WCS. A couple hands. Okay, but most people seem to have a general idea about what it is. Okay, well then I'll sort of just move on. So just quickly some motivation for why we wanted this. N-dimensional data is prevalent throughout all of astronomy, from 1D, 2D, all the way up to however many dimensions you want. For example, images, spectra, time series, so on. And it would be really great to have a common base class to do the sort of very basic things that we want to do no matter how many dimensions we have. For example, slicing and all the rest of it. So there is already some functionality out there. For example, AstroPy ND data is out there. It's a container object that links together a data array, which is obviously the main sort of feature of that. But with any data, you get supporting data or metadata with that, like uncertainties. You might have a data mask to show what data is good or bad. Of course, the data has a unit. Is it luminosity or whatever it happens to be? And then, of course, your WCS transformations, which are just a way of a standard way of going from pixels to real-world coordinates, whether that be time, wavelength, latitude, longitude, and so on. But I think that the functionality here is limited. I think it's probably a step to a greater project, which hopefully NDCube has become or will become. And that is that you can't handle this ND data object as a unified object. You can go in and you can slice and manipulate the data, but that doesn't necessarily carry through to all the other things here. So that really was what we wanted to do with NDCube. As I said, it was released in March. You can download it or install it now through Conda and pip. It provides two primary classes. First of all, you have NDCube, which is a way of handling single data arrays and the supporting data that are described by a single set of WCS transformations, and also NDCube sequence, which is basically the same thing, but for a sequence of NDCubes. So if you have images with different WCS transformations, you can handle that all as though it's one contiguous cube. Obviously, a subclass from ND data, that's why I was talking about it before, and it provides unified slicing APIs that alters the data, the uncertainty, the mask, the WCS objects. So now you can slice and interact with these objects all together at the same time, so you don't end up with mismatches between your data and your uncertainties and so on. It also provides the other thing I should mention here is that it can do that slicing, and it can handle dependent axes. Like if you have 2D and you want to slice out 1D along latitude, you can do that. That can be difficult because latitude and longitude are dependent. You need to know information about both of those in order to derive the correct real-world coordinates. It also provides a visualization mix-in, so you can quickly look at your data. And really, the philosophy behind this is to be minimalist and general. So really, it's ideal for subclassing. If you want to do spectral stuff, you don't have to use NDCube, but you can derive all this common functionality from it. So my penultimate slide here will just show you the sorts of things that you can do with specifically ND_cube. So there's a dimensions property that just gives you the length of dimensions. Again, this just helps you inspect your cube and your data in a common way. You've got world axis physical types. A lot of these we try to stay consistent with some of the things already existing in AstroPy. Get item, that's the slicing I just mentioned. You can also slice by, that should be coords, not coods, crop by cood. So you can extract your regions of interest based on real world coordinates. You don't have to be restricted by your pixels. And then these three methods here are ways of implementing those WCS transformations. Again, these two in particular are basically sort of copying the same API that already exists in other AstroPy objects. You can also, another thing I think can be very useful is you can attach extra coordinates that aren't included in your WCS set of transformations, and you can attach those to axes. So there's a huge amount of flexibility in here. And then since you've got extra coordinates, you might as well crop by extra coordinates as well. And then down here, I've just mentioned ND_cube sequence has a very similar API to ND_cube, but it has some extra functionalities to help you deal with what, instead of just it being one single data array, this whole sequence of data arrays. So I hear an alarm going off, which is great timing because this is the last slide. Here you can find out more. Here are the docs, here's the GitHub, and also I'm proposing an unconference session. And I'm really excited to hear from all you guys because I'm sure that there are uses for this beyond solar physics, which is what where I come from. So please let me know what you guys think and what you guys need, because I think that'd be good collaboration.
Let's thank Danny.
So I would like to briefly talk about Google Summer of Code. If you are a student and you are post-secondary, you are still eligible to apply. And if you're having students, it might be a good opportunity for them to join open source software development. So what is Google Summer of Code? It's a 10-week-long program to work on open source astronomy software, open source software. And for astronomy, we have Open Astronomy, which is an umbrella organization and includes AstroPy, SumPy, and quite a few smaller packages. We apply for Google. Google then, if we are accepted, Google pays the students for 10 weeks to work on specific projects. Yes, so AstroPy and SumPy actually benefited from this program quite a lot. So many of the affiliated packages got funded work on it. There are a few of us here who participated both as students and later as mentors. So if you have any questions about this, please talk to us. So this year, I'm one of the organization admins for AstroPy. Brett is here. He worked on AstroPlan as part of Google Summer of Code. And one thing I really want to brainstorm this week is whether you can help us figure out how we can reach out to more astronomy and physics students to become part of this, to apply to this program, because it's very CS focused at the moment, but it would be really ideal to get more contributors from astronomers and physicists. I think that's it. So for this year, it's already passed. Usually deadlines for organizations are around February and for students in March. And then coding starts. So Rocio is here. She will be one of our students. And coding starts in May and ends in middle of August. So it really overlaps with Northern Hemisphere summer holiday, but it's global. So basically anyone can apply, and it's remote. So you don't get to travel to the location of your mentors, but you stay at home, and everything is done remotely, which is why it really fits nicely with the open source ecosystem, because we usually work on open source packages remotely. So, yeah.
Okay, thank you very much. My name is Juan Luis again. You can follow me on GitHub over there, much more interesting than my Twitter account. Sorry for the messy slides here. They are as messy as the thing that I'm going to talk about. Okay, so I'm sure that you all saw like how SpaceX and Elon Musk launched this magnificent car over the Mars orbit, right? And it was very exciting and all of that. But I'm the orbital mechanics guy, so I wanted to simulate this orbit and see how it looked like on my computer. So I said, okay, let's go to this modern system made by NASA. Okay, it's so modern that it has a telnet interface, yes? Okay, so you get an idea of how modern it is. So you get the data, you have to define like what is the origin and what is the object that we want to follow, etc. So you get the data that at first sight it looks like this, and it looks like this. So you get a bunch of numbers and you say, okay, but where is this? Where is the reference of this? How is this located in space? So I need what we call a reference frame. Everybody knows what a reference frame is? Okay, more or less. So if you look on the documentation of this, it says ecliptic and mean equinox of reference epoch. What does this even mean? I don't understand. Okay, so I have to dissect each of these words to understand what's going on. Okay, so this can be difficult, right? So enter reference frames. I don't want to get too technical into this because I want to, give some details about the problematic of the thing and then start some discussion. But just as a summary, we have these ecliptic reference frames in AstroPy. This is taken from the official documentation of the last stable version. And you see that we have barycentric true ecliptic, geocentric true ecliptic, and heliocentric true ecliptic. But I said before that these were mean ecliptic, okay? So where are my mean ecliptic elements? I cannot simulate this orbit with AstroPy, right? So what I did was trying to fix this thing in AstroPy, which of course, in the end is all lies because the Earth is flat, okay, so nobody cares. There's some motion of the Earth that makes a difference between how do you define the plane of the reference frame. So in the end, there was a problem of precision of the ecliptic reference frames in AstroPy, which was fixed by not accounting for that special motion of the Earth, which, by the way, makes the current reference frame names wrong, okay, because they are called true ecliptic in the documentation, but in fact they are mean ecliptic by nature. Okay, so this is everything getting very messy. And I left out the center of the reference frames because, of course, I might be interested in having a reference frame that is centered on the Earth or on the Sun or on the barycenter of the solar system. And for some measurements, this doesn't make any difference because you all have angles. But when you are dealing with small distances, then this makes a true difference. So I had to fix this as well. And we left out also the obliquity, which is the exact inclination of the axis of rotation of the Earth with respect to the ecliptic plane. And in fact, I discovered a package over there that is called Bind. They're doing pulsar timing, I don't know what. So you have all these conventions for the exact angle of the obliquity. And it's not trivial because depending on which data set you choose and which standard you choose, then you have a different value for the angle, and if you get this wrong, then you have all the results are wrong. And if you want nanosecond precision, then you cannot afford to do this thing. So now what? I don't have an idea what I'm doing. We want to support both mean and true ecliptic frames because we had true ecliptic frames at the beginning, so we want to keep them. But I need mean ecliptic frames for the data that comes from NASA. I would like to support at least 2 different obliquity values, but in the end it's going to be arbitrary ones because there are more and more strange data sets coming from nobody knows where. And I want it to be centered on the Earth or on the solar system or on the Sun, which makes a combination of no less than 12 different reference frames. So if this thing was complicated before, now imagine going to the documentation and having to choose between 12 different ecliptic reference frames, okay? Nobody wants to do that. And some of which, they are just theoretical and we are not sure if they are real people using them or they are just, fictional. So what is going on? Please help me. Let's talk about it. Thank you very much.
So rather than explain what the horrible acronym up on the screen is, I'm going to tell you why you should care about the horrible acronym up on the screen. LSST is very, very big. That's Gemini up there, and that's the Gemini field of view on the top. The LSST field of view is underneath it. It's about the same size diameter. If we used every second of every ground-based telescope and space-based telescope's time for follow-up, and we will still not be able to follow every single transient source we could find. And you should better believe that the transient community is going to actually apply to the TAC for every single second of every transient telescope time there is. So you should care because you are interested in LSST and using ground-based facilities, or interested in space-based facilities and using space-based facilities. You are interested in time domain. You are not interested in the time domain, but you are interested in what LSST is doing outside when it's doing things in the time domain. Or in the next 5 years, you want a job and you want to have machine learning or big data anywhere on your CV. So the variable sky is huge and messy. There's lots and lots of different things on here. Finding anything interesting is like finding a needle in a needle stack. So the kilonova, for example, is not even on there. And we'd be trying to find one more of those somewhere in this alert stream. We'd love to use machine learning to solve this problem. But there's no actual good data set to train machine learning. So we're going to simulate the entire LSST sky. That's what we're doing with this thing called Plastic. So Plastic is taking transient models, simulating LSST conditions, using a code called SNANA. We'll be deploying it as a public challenge very, very, very soon, because there's a meeting right after this one at Flatiron where we're finalizing things. So you will be responsible for deriving features from our time series light curves for different kinds of classes of objects. You'll find that those features will probably be strongly correlated, and you'll want to do things like PCA dimensionality reduction and stuff like that. You can use things like unsupervised clustering techniques to separate out different data sets. This is using a thing called a t-SNE. Or you can use supervised learning techniques to separate out different data sets. And if anybody would like me to talk about scikit-learn sometime while we're here, I'm happy to do that. And this data set is going to be out in summer, so pretty much next month. And it will be on Kaggle. So you can not just take part in this challenge, and that number of 100 megabytes is wrong, but you'll get about 10 million objects from 3 years worth of LSST simulated data with several different transient models. And if you classify things, you can actually win money in addition to fame and glory. So thanks. You should take part in this.
So, hello. So I want to show and promote a bit the code I've been working on. So Dataproc has a friendly framework for astronomical data in multiple files and time series processing. So I'm a professor at Universidad de Chile. I started the project back in 2013 with several periods of very low activity and some other with good activity, and have been coding this with my group. 3 students have contributed considerably. So far, the work has been done with Subversion, so in a private repository, but I want to upload it to Git soon. I will be under my username DuckRojo, which an account I opened last week. So it's several thousand of lines of what I will be showing you now. So with the motivation. So before tempting you to break the code of conduct, I'm showing you with Windows, but it's not what I used to work. So all this is done in Linux, of course, and this is just to on the road to have on the road on the laptop. So the motivation was this kind of data sets. So the data sets that comes with several files. For those of you that works with ground-based observations, this could be very typical. So it includes a bit of biases, files, floods, and the science data. This was in particular for transit light curves. So lots of frames, lots of observation, one after the other. So in 2013, there was nothing to work with this. I did not want to use IRAF. So I started developing Dataproc. So for this, I created 2 big objects. One is an AstroDir. which is basically a collection of Astro files. So I just put what is gonna just a directory with the wildcards, and it goes into this container. And this AstroDir is very easy to query. For example, the fits header, just like that. It's very easy to sort. So, for example, here it was the name of the files were not related to the exposure time. So I want to sort by the exposure time, and voila, is there. So this is the object sorted, and there is the query. The header can be queried as a string also, not as an attribute. And indexing is much more than just querying with the string. You can slice. You can get an item. You can use the NumPy notation, where you can index as a Boolean array and gets you only the true values. And in the last line is just to show that every one of these is returning a new instance. And this is one of my favorite attributes, allows you to filter by the header. So I have this bunch of files in this AstroDir object, and I want to filter only those with X time, with exposure time 20, and there you go. Or only those with the Julian date of that much, and there you go. But you can do much more. So not only with an equal, so I'm borrowing the idea here from Django, where you can use, for example, greater than, and that will show you all the files with the exposure time greater than 30. Or you can use an OR construction, so greater than 29 and lower than 15, or you can use an AND construction with a greater than 5 and lower than 30. And so on. So it's very easy to from those big data set with that big set of files to extract whatever you want. And what's the Astro file? The Astro file is I'm just going to take 2 of those, and you can as well query the header. You can do math on that, basic math. So if it recognizes the plus as that it wants to work with the data inside the Astro file, so it just adds that so it's a fits file basically, no, but it extracts the data from there. All the basic math, plus, minus, multiplication, division, etc. I'm really short on time. And let me go quickly. So, you can plot, and this is one of the things that is very easy. So you can combine the files. So this is in the case of the darks, where you have darks with several exposure time, and you want to choose one with the exposure time somewhere in between. It just interpolates that. Or if you want to, for example, all the bias and median combine, and then you get the master bias. Or you can have the master flat and get the median using the master bias and median combine them, you get the master flat, and so on. So it's very easy to work with all the data that you have in several files. And I'm running out of time to show you basically what the work for this was to do transit parameters. Let me show you just a quick result. So this is the kind of results that I used it for. So a series data set that you can easily follow follow a frame through different epochs, through different frames. Yes, and I'll be happy to talk later.
Can you send out a link to the notebook?
Yes.
Okay, so I went to PyAstro conference last year in 2017, and one of the main things that I took from that conference was an idea that was thrown by Azalea about having code review sessions in your institute, having a group that gathers every week, every 2 weeks, every month, whatever works for you, and talks about code.
And I actually brought that back to the University of Sheffield, where I work, and it's had a tremendous impact on our group, and I wanted to tell you about it. So what's the motivation behind it? Well, the main motivation is that, I don't know about you, but in my case, I'm self-taught. Most of the people in my institute are self-taught. And so we don't necessarily have good coding practices. And we could do with talking about what we do and sharing our experience and what we've learned from, I don't know, Stack Overflow, or asking experts. So what we've been doing is meeting every fortnight. We've decided to only include early career researchers, so PhD students and postdocs in our group. The motivation behind that was so that people would be more comfortable sharing their code and showing their code, because it was very new in Sheffield, and we didn't want to have supervisors there potentially judging the work of people. Exactly. It's actually worked very well. And the other idea behind that is that a lot of academics don't use the same languages that students do, and they're a little jaded, and they've got teaching to do, they've got a lot of things to do, they're very busy people, and so they wouldn't be very interested in that. But early career researchers were very, very interested in this idea. And so we covered a variety of topics over the past year. We organized Git and GitHub introductions for the new PhD students and for the people that don't use code just as much. We did a lot of Matplotlib, because Matplotlib can be very tricky and have little quirks that are nice to share with people so that they don't spend 2 days trying to make it work the way you did. And I also tried to get academics to come and give us talks on things that they're very good at. We had a friend who's a statistician tell us about MCMC and how to implement your own MCMC code so that it wasn't as black boxy. We had someone come and tell us about, like tips and tricks for young developers and stuff like that. And I also designed activities to try and get people to collaborate, because it's not something we did a lot. And we wanted people to get to work together as a team. And as you might see, noughts and crosses and randomized bingo sheets aren't very astronomy specific, and there was a reason that we picked stuff like that. It's because if you have a theorist and they work on the light curve, they have no idea what they're doing. And if I have to work on an n-body simulation, I have no idea what's going on. So we wanted something that everybody could understand the basic concept of, so that we could code together as a group. And that has worked tremendously. We've had so much more collaboration, not just in the sessions, but every day we have people talking to each other, asking questions, helping each other. New PhD students aren't left on their own learning Python. And we have a repository where we put all of the tips and tricks that we've talked about during the session so that people can get back to it. And just before coming to the conference, I asked the people in my group to give me feedback on how they felt about this initiative. And some of the stuff they said was quite nice. They felt that it was very clear there was no judgment in the way that we were exposing code and talking about the code. They really liked seeing how people had very different ways to solve the same problem and learning different tips and tricks. Beginners really enjoy seeing the wide range of options, because sometimes you just don't know that something exists, and so you start coding it yourself and realize that AstroPy does it for you. People have been really enjoying sharing their skill with others and just asking questions. So Azali also suggested that we run an unconference session about it, because it could be useful for maybe your institute, or maybe you have experience in that, and we could all do with talking about it. So I'll be suggesting that to do later in the week, and if you're interested, then we can do it together.
All right. So I told you I was going to proselytize about Astroplan, and so I'm going to do that. If you're like me and you're an observational astronomer, then occasionally you get emails in your inbox that look like this, and they send you into a panic. oh, I have to observe the thing, and the thing is coming soon, and the deadline is coming even sooner, and of course I've left it to the last minute, and I need to know exactly how to plan my observations. And so there's this step that comes between that email and arriving at the mountaintop where you have to plan your observations and convince attack that you've planned them properly. And I would like to convince you not to use a black box to do that. I would like to convince you to put AstroPy in that box and use AstroPlan. AstroPlan is an AstroPy affiliated package meant for planning ground-based observations. It's AstroPy affiliated. It started as a Google Summer of Code project in which I was one of the first students, and then I later became a mentor on the project. And the main goal was to make problems like this easier. If you want to use AstroPy to answer the question, where is Vega right now? It takes a little bit of work. You need to know about how coordinates are stored in AstroPy in both space and time. You need to then specify where you're looking from and where you're looking towards and where now is in order to figure out how to look in a given direction. But that's not really an observer-centric way to answer this question. And so the point of AstroPlan is to have a wrapper around all of these AstroPy objects that give you an easier interface to answering the question, where is this star now, for example? And so with AstroPlan, that same problem would be solved by creating an observer object, and creating a target object, which can be queried from Simbad, and then asking where that target is at a given time. There are also a ton of other methods on your observer object which are useful. For example, if you're observing across many time zones, it's useful to say, is my target up right now? Or did the sun set in Australia? I don't know. Another thing that we found really useful was to introduce this concept of observing constraints, that once you have an observatory, a time, and a target list, you then need to narrow down which of your targets are observable given a list of constraints. Like, are they within the air mass limits that I care about, or are they within the pointing limits of my telescope? And so we created classes in AstroPlan that implement each of these constraints so that you could take a target list and a constraint list and figure out which targets are observable given your list of constraints. And that should save you a lot of time in planning your observations in the future. Of course, the point of that is to then build a scheduler so that you could schedule observations. This was implemented in Google Summer of Code 2016. And so now you can make crazy plots like this. These are organic plots made by a user, not by a developer, where this is an air mass plot of many different targets, and the background shading is showing you the ideal time to observe each of the targets at many different observatories all around the world so that they could figure out how to do their follow-up. And that might look like bananas to you. If that looks bananas to you, then I encourage you to join me and Azali in our unconference session later when we will be hacking to try to make this particular kind of plot more readable and legible and perhaps even closer to what you're expecting it to look like instead of like that. Thanks.
Okay, I think I will keep us on time. And I'm going to be upfront. I'm going to sell you stuff. I'm going to try to sell you stuff. So I'm Emily Rice from here, CUNY and AMNH. The first thing that I wanted to tell you about, because it's kind of related to my long-term Python and astronomy plan, is this book that I wrote that's called Astronomy Labs, A Concept-Oriented Approach. There is no code in it. That's not true. There are plots in, so it's a lab manual of 40 introductory astronomy labs for non-science majors, just in case there's anybody that is a teacher in here or wants to be an astronomy teacher at some point. This is available to you from Pearson Publishers, who are one of the biggest college publishers in the world. They publish the Bennett books and Chase and Macmillan and stuff like that. I just want to let you know about this. So the plots that are in it, we made using IDL. Other than that, the key to this lab manual is the lack of equipment and the lack of kind of black boxiness that you usually find in an introductory science lab. So I'm also proud of this nice little website I made with Squarespace. So you can either click through or scroll down through. So here's the table of contents with very short description of a bunch of the labs in a bunch of sections. So kind of introductory stuff, Earth-based stuff that you typically would do in an Astro 101 course, phases of the moon, seasons, et cetera, tools for astronomy. So we go into some kind of physicsy basis for it. This one is always really hard for some reason, even though I think it's very straightforward. Kind of very introductory quantum mechanics, images and telescopes, solar system stuff, star stuff, galaxy stuff, and cosmology stuff. So we really do all of Astro 101. Just to show you, there's a link of, or there's a list of equipment here that's really, really basic. So craft stuff, some very simple electronics, flashlights, batteries, LEDs, arc lamps, that's usually in a physics lab, very simple optics, just toys. And then some web software, so these PhET tutorials that are produced at the University of Colorado, and office supplies, and then some astro images and other random stuff. The reason that I wanted to bring this up is because this is my kind of next step career goal, is to take the principle of these and build labs for astronomy, or at least science majors, using Python as the not black box again. So I want to contribute to the AstroPy tutorials in order to learn Python and help people learn Python using astronomy, or learn, what did we decide, Kelly, was the terminology for the tutorials? Learn astronomy, now I can't remember. There was different ways that we had subdivided the tutorials, the Learn AstroPy. I'm sure there'll be an unconference session. Yeah, we have guides, tutorials, examples, and then the docs. Yeah, and so there's different kind of scopes, but those are more about learning AstroPy. These are going to be about learning astronomy, but using Python and probably mostly AstroPy as the tool. And so that's what I want to build on the principle of this for my kind of next maybe 2, 3, 4+ year project. But those labs you can have your students buy if necessary, if you are interested. And you can ask me more about them if you are interested. The other thing I want to sell you is more fun. So I also mentioned before that I'm Startorialist. I'm half of Startorialist. It's an astronomy fashion blog, but we are kind of expanding into selling stuff. So if you go to startorialist.com/archive, you can scroll through. You can see we haven't posted very much recently, but going back through the archives, we posted a lot more, especially at AAS in January. Lots and lots and lots and lots of, ooh, there's Sarah in her t-shirt right there. Yeah. Yay! You totally planned that. But the reason that I'm showing you this now is because we're starting to sell stuff at conferences, and I brought stuff with me. And Matt said it was okay. Oh, yay! I was so afraid that everybody was going to be like, what are you doing? That's what the little suitcase is. And so we're going to set it up during wine and cheese. I brought samples of stuff, but I have more at my house. And so I will go, like, if we don't have your size and the samples that I brought, I will go back and bring more. I'll have more at upcoming big conferences, AAS, DPS. We're probably going to try to go to AAAS. All the alphabet soup. If you want us to come to your specific conference, or if you want to order swag for your conference from a designer, you say, I want this particular type of thing. We also want to become the conduit between the professional scientists and the designers that are very interested in science, because some of these people, some of them are scientists, some of them are also just very science enthusiastic, and all of them are very, very talented. And it's a really fun thing to get into. Ooh, and if you want to ask me about seeing these Truvolo prints at the New York Public Library, that's a super fun story. That's my favorite. Okay, I did take the whole 5 minutes. I really didn't think I would.
Can we see this? Okay, so I'm going to keep on a kind of outreachy theme. I was lucky to be on the organizing committee and a presenter at the LIGO Open Data Workshop, which was kind of the same size as this meeting about a month ago at Caltech. Yeah, you can see my browsing history there. Where we brought in some combination of high school teachers and undergraduates, postgraduates, postdocs, professors, people who are interested in learning how to use the open public data that we have from LIGO. So if you go to losc.ligo.org, you get to this page, and it talks about the public data we have. But the interesting thing is So the outdated link that says attend Open Data Workshop. You get to this page, and then if you scroll down and you kind of know what you're looking for, which you all will do in about 8 seconds. This is the conference that we had. It was kind of similar to this, where we had some talks in the morning and some tutorials, but if you go to the link that says tutorials, you get to a GitHub repository of mainly Jupyter notebooks, which build on the existing notebooks that the Open Science Center have already put out. The first set of notebooks that were put out with the first public data releases were not particularly real-worldy. They used kind of basic NumPy and SciPy to load in some data and to do some processing in order to calculate things, which is not what we actually use within LIGO and Virgo to do gravitational wave analysis. The nice thing is that these tutorials are the software that we actually use to do our analyses, and they're using the public data, which is essentially the same data that we use to actually do our data analysis. So this is kind of real-world examples of the code and the data. So I'm just going to skip through. The important thing to read if you're going to actually try this out is there's a setup directory which talks about how to set things up in using Docker or Microsoft Azure to actually read the notebooks with all the software. This does not work on Windows on your own machine, so don't try it. But you can use Azure, which is a kind of a notebook hosting service. But then if you set up your Azure, I mean, this is what Microsoft Azure webpage looks like, and you clone the repository of the notebooks, and you get, if you go into specifically the GWPy directory, which is the software that I develop, you get presented with a list of what is 6 IPython notebooks. If you open up one of them, this is the signal processing with GWPy part 2 time domain stuff, and it goes through importing some objects, finding the GPS time of a particular gravitational wave event. You load the data, and that's what the data look like, which is kind of crazy. But it goes through in terms of looking at the frequency domain, and then doing some. If you zoom in, this is right around a gravitational wave signal, but you wouldn't really know it. But if you do some bandpass filtering, and if you do some notches, then you get to see something, and then you can keep going down into the data to actually end up with something that looks like this, which is a very clear presentation of a binary black hole signal. If you listened to my talk from this conference last year, you saw basically this kind of stuff. But the good thing about the Open Data Workshop was that we brought in more than just GWPy. We brought in something called PyCBC, which has its own, 5 notebooks, which is the real analysis software that does compact binary coalescence analysis. We also have, if I go back, tutorials on parameter estimation, and if you go to the cunningly hidden page 2, sky maps and stuff. So there's a huge amount of information. It took us 3 days to present all of the notebooks and go through all of the tutorials. But it really is a very nice repository of real code, real data examples on how to get started in looking at the kind of techniques that we use in gravitational wave data analysis. So I'm happy for people to come talk to me for the rest of the week in terms of how you can use the software, how you can build on these tutorials to teach maybe undergraduate physics or high school physics. But it really is a nice set of resources. I just want to advertise it and ask for, if you have feedback after reading them, please let me know. I also kind of direct people towards Alan Weinstein, who talked this morning. He's the interloper who wasn't supposed to be here, but he's the director of the Open Science Center. So he's the kind of ultimate resource on how we get all these stuff. I think we are going to have another one of those open data workshops next year, hopefully. So this is going to be an ongoing thing. Thank you.
All right. So I just wanted to show what I thought was kind of a fun little data visualization project that demonstrated, in the end, I think how the sort of the Python ecosystem can work together to let you get something done relatively quickly. So probably some of you know, but if you don't know, last week was the Gaia DR2 release, which is the Gaia. I think somebody already mentioned what Gaia was, but it's this big space mission that is getting all the proper motions for practically everything, is what it feels like. But a huge data release, and it prompted me to try an interesting visualization, inspired by something someone, James Davenport, said on Twitter, where he showed this neat little visualization he made a while back, demonstrating the concept of parallax, right? What parallax actually looks like. of course, this was with fake data, not actual data. So it occurred to me, maybe we can use Gaia with all its amazing proper motions and parallax information to do this with real data. And in fact, it worked surprisingly well. So I'm just going to go through sort of quickly how this the Python astronomy ecosystem works well for doing something like this. So on the day of the Gaia data release, I decided to pull some of this stuff together. There's already an existing AstroQuery module made by the Gaia Science Center Archive, or whatever they're called, that you can use to access Gaia data. The trouble was I started this at like 5 p.m. on the day of the data release, and their servers had decided to go down right around then. But it turns out there's a mirror of that data available through that Heidelberg provides, this ARI group. I forget what that stands for. But they have the same data, so it turns out I could use essentially the same interface to access a mirror of the data using the exact same code that I'd already been testing on the actual data, right? So that's this commented out part, because it turns out, then Gaia came back online the next day, but I didn't know that at the time. Now, it turns out it was slightly wrong. They're slightly different what the mirror provides and what the real Gaia data center provided, but it wasn't super complicated using existing Python standard library procedures to fix up the data that was coming out of the ARI query. That's not really that important. So in the end, it became fairly straightforward to use the same code with either ARI or the Gaia data center, Gaia archive, to just do a query that grabbed everything sort of within the surrounding 50 parsecs or 100 parsecs, right? So this is actually very readable. It just says 100 parsecs, find everything that's sort of within that space. Then let's see, I don't want to run out of time here, so there's a lot of stuff about visualizing that's not terribly important right now, other than it can give you this nice pretty thing that shows all the relatively bright stars within, this is now 50 parsecs. But the neat thing is then, because this is all compatible with the AstroPy coordinates machinery, it turned out to be fairly straightforward to just scale up the size of all the parallaxes so that it's like the Earth's orbit is a light year rather than an AU. And then you get this nice visualization right here. Right, so just from pulling all the same data down and using the AstroPy coordinates machinery and making the size of the Earth's orbit 1 light year rather than 1 AU, you can get this. And you see all of the real data centered on the ecliptic North Pole and actually going around, right? That's why the orbits are like that instead of like that. And then it's just like one line of code change using the AstroPy coordinates machinery to then switch to instead looking along, this is now rotating the view sort of facing down that way. And you can see, in fact, it goes, whoa, whoa, rather than whoa, ah. Technical terms. Yeah, exactly, exactly. But then the really cool thing comes in that actually uses Gaia to its full potential is adding in the proper motions, a suggestion from David Hogg on Twitter. So what you're seeing here is now all of the surrounding 50 stars, and you see both the parallax effect and their actual proper motion as measured by Gaia. So that's neat. But wait, there's more. Gaia also includes radial velocities, right? So we can actually use, again, this is, in what to me at least looks like the real business is sort of like these lines of code up here, using the AstroPy coordinates machinery and AstroQuery. You can do this thing where we actually get the true space motion of the surrounding all the brightest stars within 50 parsecs and their parallax effect, right? So actually it's the last one is the really neat one, right? This one. So it starts out, if we give it a second, now we're doing the whoa parallax, and then now you see the proper motion. And if you look carefully, like this cluster, the Hyades, is actually changing color just a little bit because you can see the radial velocities at the same time. And I just thought this was neat, so mostly because it was all of the Python stuff working together.
I just have this one slide. I'm heavily involved in the dark energy spectroscopic instrument. This slide is linked into the list of talks, so just go there if you want to check out any of these. DESI is a massive redshift survey, kind of similar in spirit to Sloan Digital Sky Survey, BOSS and eBOSS, with the order of 50 million objects planned. And we've been using GitHub extensively. There's our group repository there. we are primarily using an advanced form of spectral extraction, which is why the pipeline requires massive development. You can read about the paper there, but basically it's using arbitrary point spread functions and line spread functions to extract as much, every last drop of data you can from your two-dimensional spectra. As part of that process, we've learned some interesting ways that Python behaves on massively parallel systems, which I'd be happy to talk about. Second, basically Carl already covered a lot of the things that working in the GitHub environment covers for you. Things like testing, documentation, and all that stuff. I mean, he covered it already. Basically, in DESI, we were told to do that by a reviewer. That turned out to be a very good thing for us. That was several years ago, and we haven't looked back. But, you know, if you are on a review committee, you have the power to tell people that they should be using open source development tools. And finally, we have gone through all the usual Python transition pain. This is the biggest one. String valued columns in fits binary tables. But that pain is in the past. We are literally weeks away from dropping Python 2 entirely. So I'd be happy to talk about all of these topics in detail. I just wanted to give a quick overview of that. Any questions?
So I'm going to talk about CAOM, which is the Common Archive Observation Model. Let me just do it this way, in the interest of time. So, just in case people don't know me, David Rodriguez of Space Telescope. So what is CAOM? CAOM is a framework. It's a model of how we organize the metadata from various missions, telescopes, observatories in a uniform fashion so that we at Space Telescope, as you know, we have massed the multi-mission archive. We want to be able to search across all missions in the same way. So it doesn't matter if your data is infrared or optical or UV. It doesn't matter if it's ground-based, space-based, etc. You should be able to find it with the same sort of tools. That is what CAOM is trying to offer. This has been developed by CADC, and it's implemented at Space Telescope and at a variety of other observatories. So I sort of jumped in at the last moment and decided, hey, I'm going to present this. So if anyone from CADC is here, hey, cool. The model itself is on the right. I don't expect you to be able to see that or understand it in any way, but that's all right. You can go to opencadc.org to find more information about all of these different aspects. So what CAOM does is it takes the metadata from your particular files or your list of files, things like the name of the telescope, the proposal time, WCS, exposure times, et cetera, and it spreads it through a variety of sort of levels: observation, plane, artifact, parts, and chunks that describe different things. Observation can be sort of the top level information about, say, what telescope is being used. Plane can be something about the calibration level and the WCS information as well. Artifacts are the actual files, the names of the files, the locations on disk. Parts are the extensions to the file, so you can think of, if you have FITS files, each extension is a different part, and a chunk is the WCS information stored within that specific extension. There's a Python code developed by the folks at CADC that implements this all as a variety of Python classes with functionality to serialize it, that is, write it out as XML objects. So we have directories of just tons and tons of XML files that store the entirety of an observation or the metadata observation of a specific observation as a single XML file. We can just put this into a database, and we have scripts in our database known as stored procedures that extract the information from the XML and populate it to a variety of different tables. That's pretty much the gist of it. It's still being developed, but it is in use at Space Telescope. So if you ever come across things like our tab query or our API and you see references to CAOM, this is what it's referring to. And if you have more, if you have questions about how CAOM works and are interested in this, you can come talk to me at any time. Yeah, thank you.